Swayam Prabha. Digital India. Educated India.
Hello all, welcome back to the lecture on infiltration. So in the previous lecture we were discussing about measurement of infiltration. We have gone through the conventional methods of measurement of infiltration, that is ring infiltrometers. We have seen single ring infiltrometer and double ring infiltrometer. One numerical problem also solved for understanding the concepts related to the infiltration rate and cumulative infiltration. Now let us move on to the estimation of infiltration. So measurement is coming under experimental methodology. So estimation we will be making use of mathematical equations. Let us see what are the different estimation methodologies followed for infiltration. One is the empirical method. Empirical equations are there for the estimation of infiltration. Second one is the theoretical equation. So empirical equations are derived based on conducting so many experiments, and finally certain equations are proposed for finding out infiltration. And on the other hand, theoretical equations are derived based on the fundamental principles. It will be giving solutions to the flow equation which is already derived, that is we have derived the Richards equation, and which is representing the unsteady flow taking place through the unsaturated porous media. So some of the equations may be solution to Richards equation, other equations may be derived based on the fundamental laws of conservation principle, that is conservation of mass and momentum. So in today's lecture we are going to look into the empirical equations. So many empirical equations are there. When you look into journal papers, you can see a lot of empirical equations derived for the estimation of infiltration. I am only presenting some of the equations which are commonly used or which are present in the textbooks. First one is Kostyakov equation, then Horton equation and Halton equation. So these are the three empirical equations which we are going to see in this lecture. And coming to theoretical equation, that is which are developed based on the fundamental laws, one is Greenamt equation and second one is Philip equation, that we will see in the coming lectures. So let us start with the empirical equations. First one is the Kostyakov equation. In this, a relationship is developed as a power law for the infiltration rate. So infiltration rate is expressed by means of a power law. The equation is given by f of t. For infiltration rate we were using the notation of small letter f. So f of t, that is a function of time, infiltration rate is a function of time. F of t is given by k t to the power of minus alpha. F of t is equal to k t to the power of minus alpha. And for cumulative infiltration, we know the relationship between the cumulative infiltration and the infiltration rate. Once infiltration rate is known to us, after integrating that particular expression, we will get the cumulative infiltration. Same thing has been done over here. So capital F of t, that is nothing but our cumulative infiltration, is given by the expression kk divided by 1 minus alpha t to the power of 1 minus alpha. This we can obtain by integrating the infiltration rate equation. In these equations, Kk and alpha are empirical positive constants and alpha is always less than 1. So, Kostyakov equation is representing a power law corresponding to infiltration rate small f of t, and capital F of t we can derive based on the infiltration rate curve. After integrating that, we will get the cumulative infiltration, and the empirical positive constants are Kk and alpha. Now, you look at the equation f of t Kk t to the power of minus alpha, it is f of t is equal to Kk divided by t to the power of alpha. So, in this case, when the time is infinite, that is for long times, when t is very high, what will be the condition? T is very high. In the denominator, we will be having a very high value. So, f of t will be approximately approaches to 0. For very large times, infiltration rate will be 0. On the other hand, very small time, when time t is equal to 0, if t is equal to 0, denominator will be having 0, 0 and infiltration rate will be infinite. So, when time t is equal to 0, infiltration rate is infinity, and when t is very high, infiltration rate is 0. This is not practical. Very high value of infiltration is possible, but infinite, that way we cannot tell. There is a certain capacity, there should be a certain value corresponding to infiltration rate, even in the beginning, even if the soil is very dry. And if the soil is saturated, fully saturated, still there will be an infiltration taking place. Infiltration will not be 0, it will be very small value. So, there are certain approximations to be taken care in this case. So, we cannot consider the infiltration to be taking place for a long time. We will stop the experiment when the infiltration rate, we will take the value as the infiltration rate or the steady state value as the hydraulic conductivity value. So, this equation is valid till the time Ft becomes equal to saturated hydraulic conductivity of the soil. Now, this equation is having two coefficients Kk and alpha. So, these coefficients need to be determined. So, next let us see estimation of two coefficients from the measured infiltration data. This is our equation. Cumulative infiltration f of t is equal to Kk divided by 1 minus alpha t to the power of 1 minus alpha. Now, what we are going to do? We are going to fit a straight line to the data ln f of t and ln t. We are having cumulative infiltration data corresponding time also. We will be taking natural logarithm to these data points ln f of t and ln t. So, if we are taking ln f of t, the equation takes the form ln Kk divided by 1 minus alpha plus 1 minus alpha multiplied by ln t. So, this is in the form of a equation of a straight line y equal to mx plus c. So, here y is ln f of t and then comes the x is ln t. So, 1 minus alpha is the slope, m is 1 minus alpha and ln Kk divided by 1 minus alpha is the intercept. C is represented by this particular term ln Kk divided by 1 minus alpha. So, once we are having the data, we will be taking the natural logarithm to cumulative infiltration and also time, that we will be plotting, and after that we will be fitting a straight line to those data points, and from the slope and the intercept values we can calculate the coefficients corresponding to Kostyakov equation. Next equation is Horton's equation. This equation is also very commonly used for finding out the infiltration rate and cumulative infiltration, but we should be aware of the parameters corresponding to Horton's equation. So, let us see how this equation is looking like. this is proposing an exponential relationship for infiltration rates observed under ponding condition. So, we are having a positive head of water, or take the example of a ring infiltrometer, we are maintaining a level or water is added to the infiltrometer that is getting infiltrated into the ground. So, here in the development of Horton's equation also, one assumption is that sufficient amount of water is ponded on the surface, and also this is providing an exponential relationship. And infiltration begins at time t equal to t naught with the rate f naught. So, you can compare with Kostyakov equation. Initially at time t equal to 0, it was giving an infinite value. So, in order to overcome that, if we are using this equation, it is starting with a some rate f naught and exponentially decreases until it reaches a constant rate f of c. So, in this case, initial infiltration rate is there, that is represented by the notation f naught, and it is decreasing, exponentially decreasing and finally reaching a constant rate f of c. The equation is given by f of t is equal to f of c plus f naught minus f c e to the power of minus kt. So, this particular term f of c, constant term is there, steady state infiltration value is there, that is as time elapses or time becomes large, it will be attaining a constant rate of infiltration, and in this case the second part is having the exponential relationship. So, the curve will be looking like this. Infiltration rate, if we are plotting infiltration rate along the y axis and time along the x axis, you will get an exponential curve, and in this f of t is the infiltration rate at any time t. As time changes, we will get the infiltration rate corresponding to that particular time if we are using the expression f of t, and f c is the steady state infiltration. F c is represented by this. So, f c is the steady state constant infiltration rate. As the time increases, finally a stage is reached, a steady state infiltration will be taking place within the soil. So, that is represented by f c. Then f naught is our initial infiltration rate, that is the initial value. Initially, whatever be the soil condition, what can be the infiltration rate, that is represented by f naught. It is not an infinite value in this case. And k is the exponential decay constant, which is having a unit of 1 by time. That is depending on the soil characteristics and vegetation cover, where the infiltration is taking place, in which soil the infiltration is taking place. This k value is depending on those properties. This is a most widely used equation for calculating infiltration rates. So, here in this case, the advantage is that the limitation which we have seen in Kostyakov equation is not coming into picture, because here we are having an initial infiltration and also finally a steady state infiltration rate. Relationship between the infiltration rate and cumulative infiltration is known to us. Just integrating the infiltration rate curve will be giving us the cumulative infiltration. So, this is our infiltration rate curve, that if we are integrating with respect to the time limits, we will get the cumulative infiltration. Capital F of t is given by integral 0 to t small f of t dt. We will be just substituting for small f of t over here and integrating between 0 to t, and it will be taking the form capital F of t is equal to f c t plus f naught minus f c divided by k multiplied by 1 minus e raised to minus k t. So, after applying the limits, we will get the final expression for cumulative infiltration given by this equation. Now, let us move on to finding out the Horton's parameters from the measured infiltration data. This is our infiltration rate equation, Horton's equation for infiltration rate. So, here some rearrangements of the terms which are present in the equation will be done. So, we are writing Ft minus Fc is equal to F naught minus Fc e to the power of minus Kt. After that, we will be taking logarithm, natural logarithm. So, ln f of t minus f of c is equal to ln f naught minus Fc plus ln ab is ln a plus ln b plus ln e to the power of minus Kt. And again we can modify this particular term ln e to the power of minus Kt. It will be taking the form like this, that is ln f of t minus f of c is equal to ln f naught minus Fc minus Kt. Plot a curve ln f of t minus Fc versus time. So, this will be again we will be getting in the form of y equal to mx plus c. So, from this we can find out the Horton's parameters. Once it is plotted, we will be plotting a best fit straight line which is passing through those points. You can see the graph, we are having the ln f of t minus f of c along the y axis and time along the x axis. So, these black dots are representing our terms corresponding to ln f of t minus f of c. After that, we are fitting a straight line through these points, that is represented by this red dotted line, and those dotted line is represented by the equation y is equal to this particular equation. It is in the form of y is equal to mx plus c. So, if we are comparing, we can understand that the intercept gives ln f naught minus Fc and the slope gives the Horton's parameter k. This is y equal to mx plus c, instead of mx we are having kt. So, the slope m is giving us the Horton's parameter k. So, by this way, if we are making the plot ln f of t minus f of c versus time, it will be giving us Horton's parameters. So, here there will be a confusion coming from where we will get Fc. We are having the cumulative infiltration. If we are plotting the finding out the infiltration rate, finally as time elapses, you can understand that infiltration rate value is not changing with respect to time. It will be attaining a constant rate. That value can be considered as f of c. So, by making use of these things, you can get the Horton's parameters. Now, next equation is Horton's equation. In Horton's equation, some more factors are taken into account. That is, it is based on the soil water storage, surface porosity and plant roots, which is having major influence on infiltration. If plant roots are more, it will be creating some extra pores, macro pores within the soil, that will be aggravating the infiltration rate. So, that is also taken into account while deriving Horton's equation. So, this can be applicable to agricultural areas. Agricultural areas, more plant roots will be present. So, this will be giving more reliable answers. So, f of t is given by f of c plus ICG IP SA to the power of 1.4. Let us see different terms one by one. ICG is the crop growth index defined as the maturity of the crop, and IP is the porosity index. SA is the available moisture storage capacity in the soil layer, which is a function of time. So, you imagine soil layer means upper layer of the soil. This is considered as the plowing layer also. So, within that, if this is L, so that much depth of soil, that is the upper layer thickness is considered as L, that much soil will be having some available moisture storage capacity. This SA is calculated based on the upper soil layer. So, how much is the available soil moisture storage capacity within that plowing layer or the surface layer will be calculated. That will be a function of time. So, it can be obtained by multiplying the depth of the surface layer with the moisture deficit. Now, what is meant by this moisture deficit? Moisture deficit is nothing but the difference between the saturation moisture content and the actual moisture content at any time. Maximum how much it can go? Theta can go up to eta. That is the saturation moisture content. But always it will not be at the maximum level. The soil will be at the initial moisture content. So, soil moisture deficit is delta theta, that is equal to eta minus theta I. Theta I is nothing but the initial soil moisture. So, that difference is responsible for storing extra moisture, extra water. So, that is why that delta theta is coming into picture, that is the soil moisture deficit, that is nothing but the difference between the maximum, that is eta, maximum soil moisture content can go up to porosity eta, and initially itself soil is having certain moisture content, that is represented by theta I. So, the soil moisture deficit is represented by eta minus theta I, and SA, that is the available storage capacity, is obtained by multiplying that soil moisture deficit with the depth of soil layer, depth of the surface soil layer or the plowing layer. So, this way we can get different parameters, and by making use of these values from literature, you can calculate the infiltration rate. So, that is all about the different empirical equations. So many empirical equations can be seen in literature, but some of the equations only I am covering here in this particular course, which are taken from the textbooks. The relevant textbooks are given over here as references. So, here we have seen different equations such as Kostyakov equation, Horton's equation and Holton's equation. These are empirical equations. In the next class, we will move on to the theoretical equations, which are derived based on the fundamental laws. So, for today I am winding up. Thank you very much.